So number one, if an object is moving at a constant velocity to the east, what do we know about our forces? Anytime it's moving at a constant velocity, no matter what direction, your forces are going to be balanced. For number two, if an elevator is moving upward with decreasing velocity, the direction of the acceleration. So let's think about moving upward as a velocity, upward velocity. Decreasing velocity means it's getting slower, so that would be an acceleration down, because these two have to be in opposite directions if it's getting slow. So acceleration down, moving downward with decreasing velocity, so getting slower, that would be, again, acceleration in the opposite direction, so that would be an acceleration that is upward. If an elevator is moving down with increasing speed, getting faster and faster, acceleration in the same direction, that would be downward acceleration. Moving upwards, getting faster, increasing velocity, getting faster, that's an acceleration upwards, that would be an upward acceleration. How do you find the weight of an object? Weight is just mass times gravity, or we could say mass times like 10 or mass times 9.8, those all work. We have a student using a string to pull a box across a frictionless surface. That's like a force pulling this way. If the angle is increased, we want to know what would happen to the normal force and the acceleration. So what if the force was instead upwards like this? So let's think about the forces. We have the force of gravity, we've got the normal force, and then we've got this force, which is like the y direction and in the x direction right here. If I increase the angle, then I'm increasing the y force and decreasing the x force, because a bigger angle is going to be more up than to the right. So then if I increase this force, because these two still have to add up to the exact same gravity force, so because Fy plus the normal force have to add up to the same, this stayed the same, but I just increased this run right here, that means the normal force is going to decrease. So you could say decreases. What happens to the acceleration? What happens to the acceleration of the box? Well, the acceleration comes from the sideways force, because that's the net force that's causing it to accelerate sideways. If I increase the angle, I have less acceleration right here, so this is going to decrease as well. Right, we've got an inclined plane, and because we have our forces along like this, we're going to take this mg, this weight force, and we're going to break it up into the components A and B. Which component is A? Well, A, the one that is along the ramp, would be mg sine of the angle. The component of the weight that is across from the normal force, B, that would be mg cosine of the angle, because those are just something to memorize. That's just something to memorize. Across from the normal force is mg cosine. Along the ramp, going down the ramp, is mg sine. A block of mass m is at rest on an inclined plane with a coefficient of static friction us. The force of friction holding up the block must be equal to. So let's think about. We've got our mg cosine right here. We've got our mg sine. And this is my normal force, and this is my friction force. Well, if it's at rest, that tells me my forces are balanced. So I for sure know the force of friction must be equal to mg sine. That's got to be true because they're balanced. So we can cross off D and A because they don't include mg sine. Now it's also, might be tempting to use the mu Fn, where mu is the mu s that it's saying, and Fn is mg cosine of the angle. But this is not actually necessarily true, because this is a greater than or equal to, force of friction less than or equal to. Is a less than or equal to equation. So your force of friction actually could be less than this. In fact, a lot of times, right, if you've ever tilted something, you get to the angle where it starts to move, but at other angles, the force of friction is less than that. It's holding it in place. So the only one that was absolutely must be equal to is B. It might be equal to the mu mg cosine of the angle if it's right before it starts to slide, because the mu mg cosine of the angle is actually the maximum static friction that this one can have. I don't know that it's at the maximum. It could be well before the maximum. Alright, we've got stacks of boxes as shown in an elevator moving upwards. The mass of the boxes are in terms of M. How does the magnitude of the force exerted by the top box on the bottom box compare with the magnitude of the force exerted by the bottom box on the top box? So top on bottom compared to bottom on top, those are the exact same force. So the two magnitudes are always equal. It doesn't matter if they're accelerating or constant speed or if they're different masses, those two have to be equal to each other. Assume the elevator is moving at a constant speed. So that tells us that our forces would be balanced. Consider the bottom box in the stack that has two boxes of mass M. So I have a 2M and a 2M, and we're drawing the free body diagram for this guy right here. Alright, so we have, of course, the force of gravity of the box, the 2mg. And then because we're talking about the bottom box, we also have the force of the top box on it, pushing it down. And it told us to call that F box. So it has the box pushing down. And then the floor is going to push up on the bottom box, and it has to be greater than the two of these. So the only one that matches this is C. I've got the weight of the box plus, or weight of the box we're talking about, plus the weight or the force of the other box pushing down on it, and then the floor pushing up to balance both of those forces out. Assume the elevator has upward acceleration, so now it's accelerating up, which means you have a net force in the upward direction. We're talking about the stack that has just M, and we're looking for the top box by the bottom box. So we have, of course, mg, and we have the force that we're looking for of the bottom box pushing up. So if these are my m's and, sorry, that was pulled down. If this is M and M, this is the free body diagram we're drawing it for, and this box is the force that it's pushing up, is the force that we're looking for right here. So if we're drawing just for this guy, it doesn't have a box on top of it, it just has its own weight and then the box below it pushing up. And we know that this is a greater force because it's accelerating this way, so your net force is just the force you're looking for minus mg. This minus this would give me my net force. Well, net force is just mass times acceleration, so I have mass times acceleration equals F minus mg. So add that over, ma plus mg.